our wall, our parallel fence. The beam will attach to the wall, clear the fence, and then be fastened to the ground. So let's suppose that we're going to fasten it to the wall right here on the edge. It'll clear the fence and hit the ground. So that could look, for example, like this. Or it could look, for example, like this. Depending on how high we place it on the wall, we're going to get a different length beam if it clears the fence and then gets attached to the ground. We're given the distance between the wall and the fence and the height of the fence. Okay. Minimize the length of that red beam. So our length can be a function of this variable which changes, or the length of that beam could be a function of the angle, which is a variable that's changing. So we have options. Which one you use, we'll just change the algebra a little bit. I don't know, I think I'll start with x and see how that goes. We really only need to work with one picture, so I'll work with this one, and we need to express the length in terms of x if we can. All right, well, somehow we're going to use these similar triangles. Not sure how yet, but let's figure that out. Pretty obvious first step would be the Pythagorean theorem with this right triangle. The hypotenuse will be the square root of that sum. And now let's find an expression for this segment so that we'll have an expression for the entire length in terms of x. All right, using the similar triangles, let's take the ratio of hypotenuse to long leg. So for the big triangle, the hypotenuse to the long leg is the unknown plus the root, hypotenuse divided by 4 plus x. And for the little triangle, hypotenuse to the long leg is the root divided by x. So the length that we're looking for is from here to here, which is right there. So we just really need to solve for the numerator on the left side. And that's equal to the right side times 4 plus x. We have a function for the length of our beam, and it's in terms of just one variable. Now, I don't know about you, but if I'm not using my calculator, I'm not really looking too forward to finding the derivative of this, because for the optimization problem, we have to set the derivative of this function equal to 0. So I'm going to take a look at what this problem would look like if our variable, instead of being x, was theta, this angle of elevation right here. All right. In our little our little red right triangle, sine of theta is 5 over the hypotenuse, 5 over c. So c is equal to 5 over the sine of theta. Now let's do tangent of theta. That's opposite over adjacent, so it'll be 5 over b. So b will be equal to 5 divided by tangent of theta. All right, how is this going to help us? Let's set up a proportion with our similar triangles. The large hypotenuse divided by this bottom leg will equal the ratio of the small hypotenuse divided by its bottom leg. So the length of the beam divided by 4 plus b, which in b is 5 over tangent or 5 cotangent. That's equal to the hypotenuse divided by b, which is 5 divided by sine or 5 cosecant divided by b, which is, again, 5 cotangent. All right, let's solve for L, and we'll get a different function for L dependent upon the one variable theta. These 5's divide out, and we multiply both sides by 4 plus 5 cotangent of theta. Now let's use our quotient identities to simplify all this stuff. So when we divide by cotangent, we're dividing by cosine over sine. So if we're dividing by cosine over sine, we're multiplying by the reciprocal sine over cosine. And cotangent is obviously cosine over sine. So things work out nicely here. And our length of the beam is 1 over cosine of theta times 4 plus 5 cosine of theta, or sine of theta. So when we distribute the length of our beam is 4 over cosine, and then when you multiply by the second term, it's 5 over cosine because the cosines cancel out. Sweet. So we can represent the length of our beam in terms of x or in terms of theta. So the question then becomes to find the shortest length of this beam to minimize the value of L. Would you rather set the derivative of this function equal to 0, or would you rather set the derivative of this function equal to 0? For me, I'm leaning this way. I'm going to do that then. What is L prime of theta? And let's set that equal to 0. So the derivative of secant is secant tangent, and the derivative of cosecant is the negative cosecant cotangent. All right, we set that equal to 0. We'll use the quotient identities again. Let's try to simplify all this. So we have 4 sine of theta over cosine squared minus 5 cosine of theta over sine squared of theta, all equal to 0. Which brings us to there, which brings us to, how are we going to solve that? Maybe this is a calculator problem? And doing that with the calculator, it's when theta is about 0.823. And at that point, the length of our beam would be approximately 12.7 feet. If we had tried doing it with this function, I don't think it would have been any easier. But we could quickly try it. The derivative of the first function, if we treat this whole thing right here as the first function times the second, plus the derivative of the second times the first, that gives us, using the quotient rule, we get this big massive derivative of that. Numerator times x minus the derivative of x times the numerator, all divided by the denominator squared. And then times 4 plus x, plus the derivative of 4 plus x, which is 1, times that term. And we have to set this equal to 0 and solve. Just doing some algebra. I'm going to multiply both sides by that square root. So we'll get x squared minus I think I like the trigonometry better. I'm going to keep going here. Combining like terms after this. Alright, well this just turned into a quadratic with no x terms, so square root of 100 over the square root of 3, which is 10 over the square root of 3, or 10 root 3 over 3. Alright, so if I plug that into my length function, using my calculator, I get a length of about 12.929. Alright, well that's close, but I know when I look at the answer key, this was the right answer. So I must have made a mistake somewhere in here, and I preferred the trigonometric way. And oh my gosh, I think I'm gonna stop here.